Hello, this is Dr. Hassan with Innovate, and this is lecture number 55, Derivation of State Graph, of Chapter 9, Design of Synchronous Sequential Networks of the Cross-Digital Logic Design for Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in digital logic design, however, there are many books related to the subject. In Chapter 9, there are 4 steps in the design of synchronous sequential networks. Namely, the first step is the derivation of the state graph. This is a very important step. Without it, we cannot design the system or the machine. The second step is the reduction of state graph or the state table. Then we have to find the best state assignments, which really will yield the lowest cost and the lowest number of gates to be used. Then we go to the implementation process where we choose the number of flip-flops and the gates, or if we wish, we implement with VHDL design and we implement the network on PLD like complex PLD or FPGA. Guidelines for derivation of state graphs. From the problem statement, determine the number of inputs to the network and the number of outputs from the network, and you must understand the problem in details. Construct some sample inputs and output sequences to be sure that you understand the problem statement. Every network has an initial state. Draw a node representing the initial state of the network, and often we refer to the initial state at a 0, A. Determine what sequences or groups must be remembered and set up states accordingly. You will need to add one state or node to remember one bit in an input sequence. A table next to the state graph of added states and sequences received and remembered should prove to be very helpful. 6. Each time you add an arrow to the state graph, determine whether it can go to one of the previously defined states or whether a new state must be added. 7. Check your graph to be sure that there is one and only one path arrow leaving each state for each combination of input variables. That is, there is one input variable. There must be 2 paths leaving each state. And if there are 2 input variables, there must be 4 paths leaving each state, and so on. This is very important step to be sure that the diagram, the state graph, is complete. So every node or every state will have number of arrows leaving the state, and the number of arrows will be equal to the number of variable iterations. So, for instance, if we have a single variable, x is 0 and x is 1, so there will be 2 arrows. If there are 2 variables, there will be 4 for x1, x2, 0, 0, 0, 1, 1, 0, and 1, 1. When your graph is complete, test it by applying the input sequences constructed in guideline number 2 and making sure that the output sequences are correct. If the output sequences are incorrect, you must go back and repeat the previous guidelines because your state graph is wrong and you have to redesign it. So those are really the main important guidelines for derivation of state graph. So you initiate a state to remember the input sequence. Okay, if you need to remember, for instance, 4 bits of the input sequence, so you may need actually a number of states to do that. And we will take 2 examples, one for Mealy, one for Moore, to explain the principle of building the state graph or deriving the state graph for a machine. The first example, we will talk about Mealy sequential network sequence detector. Design a Mealy synchronous sequential network, one input X and one output Z as shown in the block diagram here. We have one input X and one output Z, and we have the clock to synchronize the flip-flops. And as shown, acting as a sequence detector to detect the sequence 1001, including overlap. Therefore, the input sequence 1001 will produce the output Z is equal to 1, coincident with the last one or the least significant bit in 1001. Why so? We assume here that the most significant bit in the input sequence enters the network first, and the most significant bit in the output sequence exits the network first. Additionally, the network does not reset when a one output occurs, since the last one input should be remembered by the network. So the network will not reset. Okay. So we know now the conditions of the machine, and we have the full statement. The first step, we have to generate the sample of input and output. Following the guideline, it is evident from the problem statement that the network has one input X and one output Z. A typical input sequence and corresponding output sequence will look like this. So this is assumed. We assumed really the input sequence 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 1. This is the sequence that we are looking for here. 1, 0, 0, 1, then 1, 0, 0, 1. So we have an overlap. Okay? 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1. So if we look at the output Z, we have 0, the output will be 0. Input 0, the output is 0. 0, 0, 1, 0, 1, 0, 0, 0, 1, 0. Then we have a 0, 0, 0, 0. Then here, this 1 will trigger output 1 because we detected the sequence that we are looking for, which is 1, 0, 0, 1. Then again, we have 1, 0, 0, 1, and the output will be also 1. So Z will be 1. Then we have 0, 0, 0. Okay, then when we have 1, the output is 0. Then we have 0, the output is 0, 0, the output, and this one will trigger another 1 because we detected the sequence again, 1, 0, 0, 1. So the sequence has been detected in this example 3 times. And the output accordingly will have 3 ones. Now, how we get started? We will start constructing the stated graph with a reset state as 0. Always we start with a 0. Now, which corresponds to having received no inputs. If we are in we call it the reset state as 0. If we are in the reset state as 0 and a 0 input is received, the network must stay in as 0 since the input sequence 1001 does not start with 0. So since actually the sequence 1001 does not start with 0, I don't need to remember the 0. So I will stay in the reset state as 0. And since it is a Mealy, we have 0/0, which is x/z. That means that the input is x is 0 and the output will be 0. Accordingly, we sketch actually a small graph here, state and the sequence received. So S0, we have the reset state. We have no sequence received. Now, once I am in S0, and let's say I received a 1. However, if a 1 is received, we must go to a new state S1 to remember that the first input bit 1 in the input sequence 1001. See, I made it bold because it is really the first bit came in to the network is the most significant bit of the code. Has been received. As shown, the labels on the graph again are in the form x/z. And now when once a 1 is received again, the output will be 0, but I have to remember this one, so I will go to a new state, which is S1. So S1 remembers the sequence 1, remembers only one bit 1. The adjacent table to the partial state graph shows the states and the corresponding sequence received and remembered. Sketching this table is optional. However, it is very helpful, especially for complicated state graph derivation assignments. Now, let's go to the next step. When I am in a state S1, if we receive a 0 in a state S1, if we receive a 0, the network must change to a new state S2 to remember that the first two inputs 1, 0. So the desired sequence 1, 0, 0, 1 have been received. So I am in S1, S1 remembers 1, but S2, I will go to S2 if I receive a 0, and the output accordingly. So if X is 0, the output Z will be 0, but I have to remember this, so I go to a new state, which is S2. So S2, the sequence received in S2 is 1, 0. Okay, let's go to the next step. Now, if I am in S2 and another 0 is received, if I am in state S2, the network must change to a new state S3, okay, to remember that the first 3 inputs were received, which is 1, 0, 0. So if I am in 0, I will get what? I will go to S3, because again, S3 here will remember 1, 0, 0. So to a new state. Now, if a 1 is received in state S3, the right sequence 1, 0, 0, 1, 1, 0, 0. So we have 1, 0, 0, 1, 0, 0. If 1 is received in state S3, then what we will do? Do we go to a new state or do we go to an existing state? We ask this question. If 1 is received in S3, the right input sequence 1, 0, 0, 1 is complete, and the output Z should be 1. The question arises whether the network should then go to a new state or back to S0, S1, or S2. Since the network is not supposed to reset when the output 1 occurs, hence the network will not go back to the reset state S0. The network cannot go back to S2 either, since S2 remembers the sequence 1, 0. However, since the last one is the desired sequence 1, 0, 0, 1, can also be the first one in a new sequence, which is overlap, the network must return to S1 because S1 remembers the 1. So we go to S1. So from S3, we go to S1 because S1 again remembers the last bit of the sequence, which is 1, to allow overlap. Since the last one is the desired sequence 1, 0, 0, 1 can be the first one in the new sequence, which is overlap. So the network must return to S1 since S1 remembers 1 as shown. So here, let's start all over again. I am in S0. I received 1, I have to remember this one, so I will go to S1. I will receive a 0, I have to remember this 0, so S2 will remember 1, 0. I have another 0 in my sequence, which is the second 0 in the sequence. I have to go to a new state, which is S3. Now with S3, okay, I have to go to S1, since I will remember, so S1 will remember the last one, because S1 remember the last bit in the input sequence 1, 0, 0, 1, so I will go to S1. So when I go to S1, So 1/1, because Z must be 1, because the sequence 1001 is recognized. Now, actually, I still have really a partial map. So I have to complete the map. To complete the map, every state must have two output arrows. One for x is 0 and one for x is 1. So I am done with S0. But S1, I have one arrow output. It is 0. What will happen if S1, if I received 1, 0, if I received 0, 1? For an instance, S2 has one output arrow which is at 0. So what will happen if I received 1, 0, 1 from S2 at S2? Okay, so we have to finish actually the graph by doing the following. To complete the state graph, if a one input occurred when in the state S1, the network will stay in S1 since the sequence is simply restarted and S1 remembers 1. So if I receive, for instance, multiple ones, 1, 1, 1, 1, 1, 1, I will stay in S1 to remember the first bit of the sequence 1001 because S1 remembers 1. Now, if a 1 input occurs in S2, where do we go? So I received 1, 0, 1. Now, if I received 1, 0, 1, the 1, 0 will have no value because I will remember the last one, so I have to go back to S1. So if we received 1, 0, 1, we must go back to S1 to remember the last one. If a 0 input occurs in S3, so what we get here, if a 0 occurred in S3, it means I received 1, 0, 0, 0. So the 1 will have no value to remember anymore. So the sequence get messed up, in other words. So at that time, I have to go to the reset state. So and must reset the network if a 0 input occurs in S3, we have received 3 zeros in a row and must reset the network to state as 0 since 0, 0, 0 is not part of the desired sequence 1001. And going to one of the other states shall lead to incorrect output. Hence, the complete state graph is shown. Okay, so let's have a review of what we did. The sequence that we need to remember 1001. And once we receive 1001, the output will be 1 and we will allow overlap. So I will start with the state as 0. If I receive thousands of zeros, I will stay in as 0, which is a reset state. But if I receive 1, I have to remember this one because this is the first bit in the sequence 1001. So I go to state S1. So S1 will remember 1. Now, if I receive another 0 after the 1, I have to go to a new state S2 to remember 1, 0 because the 1, 0 is part of the sequence. Now, if I receive another 0, I have to go to S3. So because S3 will remember 1, 0, 0. S3. If I receive another 1, I will receive the complete sequence 1001 and the output here will be 1. Okay, and I have to go to S1 to allow overlap to remember the last one. So S1 goes remember the 1, the first bit in the sequence, and it happened to be the last bit in the sequence here. So I have remembered the 1 because S1 remembered 1. So in case if I receive 1001, so you will get an output Z again, and so on and so forth, this loop. Now, this is partially the graph, the state graph partially completed. Every state, every node must have two outputs, one for x is 0 and one for x is 1. So I'm done with S0. In S1, if I receive multiple 1, like 1, 1, 1, 1, 1, so since S1 remembers only 1, so I will stay in S1. S2, remember 1, 0, 1, 0. But if I receive a 1, I need to remember only this 1, which is the initial bit of the sequence, 1001. So I got to S1. However, in S3, if I receive 1, 0, 0, then another 0. So this sequence 1, 0, 0, 0 will not be useful at all. I need to remember nothing. So I go to a 0 to the reset state, and the output will be 0. And this is will finish the design of the state graph. Once I have the state graph, actually, I can have the state table in a second. Now we will repeat the same problem with more sequential network for a sequence detector. We will derive the state graph for a more sequential with an input X and output Z. The output Z is 1 if the input sequence X is 1001 is detected. Again, we have the typical input and output sequence. Except here in the more, as you remember, we shifted the output sequence Z to the right by 1 bit to emphasize that more network, for a more network, an input change does not affect the output Z immediately. Okay, so there's a delay by 1 o'clock pulse, and we have seen it in a previous lecture. But Z can change after the next clock pulse. The initial 0 in the output sequence is associated with the reset state. So we have 0. So 0, 0, 0, 0, 0, 0. Then when we have 1, 0, 0, 1, I will get an output 1 shifted by 1 position. Then again we have 1, 0, 0, 1, and again I have another output 1, and I can see 1, 0, 0, 1 will have an output 1 again. So this is actually, we start construction of the Moore state graph as shown with the reset state as 0. Now, we start construction of the Moore state graph as shown with the reset state as 0. As we associate a 0 output with this state, if you get a 0 input and a 0, the network will remain in S0 since the desired sequence 100 does not start with a 0. However, if we get a 1, we have to remember this 1. So in this case, we know we go to a new state, which is S1. To remember the first bit in the desired input sequence. The output for S1 is 0, since the complete desired sequence is not complete yet, is not received. So, again here, we have S0 and the output is 0. So S0/0. If I receive many, many zeros, I will stay in the reset state as 0. If I receive a 1, this is the first bit in the input sequence. I have to remember this one, so I go to S1 and the output is 0. And this table also will show you that S0 is the reset state and S1 remembers 1. Now, when in state S1, if we receive a 0, the network must change to a new state S2 to remember that the first two inputs 1, 0 of the desired sequence 1001 have been received. As shown, again, the output associated with S2 is 0, since the complete desired sequence is not yet recognized. So S2 will remember 1, 0. So again, 1 remembered by S1 and 0 will be remembered by S2 or S2, or the machine will remember now 1, 0. Now, if we receive another 0 in S2, okay, if we receive a second 0, the network must change to a new state S3 to remember that the first 3 inputs 100 of the desired sequence 1001 have been received, as shown. Again, the output associated with S3 is 0, since the complete desired sequence is not received. So S3 will remember now 100. Now, if I am in S3 and I receive another one, so if I receive another one, I will go to, the network must go to a new state S4 to remember the last bit of the desired input sequence. The output associated with S4 is 1. The output associated with S4 is 1. Since all the 4 bits of the desired sequence was received, the sequence 1001 was recognized. Now, really, the thought that if I receive a 1, to go to any of these states does not exist because the output must be 1. So I have to go to a new state, which is S4, where the output is 1. Now, so partially I finished actually the state graph. Now I have to complete the state graph by applying the rule. I have to have 2 rows, okay, output from each state. Now, if I am in S1, and a 1 input means that we have received multiple ones, like 1, 1, 1, so I will stay in S1. So if I receive multiple ones, I will remain in S1. Because S1 remembers 1, all we need to remember the first bit in the sequence, desired sequence 1001. Similarly, if 1 input is received in S2, we must go back to S1 to remember the first bit of the desired sequence, okay, because 101 will be not a desired sequence. All I need to remember the 1, okay, the last one. So if I am in S2 and receive a 1, I will go to S1 because S1 will remember 1. Now, if I am in S3, if a 0 input received, the network must go back to the reset state. But because received if I am in S3, what I will receive? 1, 0, 0, 0. Now, 0, 0, this is useless. 0, 0, 0 is useless to me. I need to remember nothing now. And I will go back to the reset state as 0. To the reset state as 0. Now, to start all of, while if I am in S4, and a 0 is received, where do we go? If I am in S4, and a 0 is received, S4 actually does not have any output at all. So we have to study both the 1 and the 0. So if a 0 input received, the network will go back to S2, since S2 remembers the sequence ending with 1, 0. So if a 0 is received, I will go to S2 because S2 will remember 1, 0. So I will have, in this case, 1, 0, 0, 1, 0. So I have to remember the 1, 0. The 1, 0, and S2 remembers the 1, 0, so I will go to S2. Okay? Now, if a 0 is received, the network will go to S2 since S2 remembers the sequence ending 1, 0. However, in S4, if a 1 is received, so the sequence will be 1, 0, 0, 1, 1. I need to remember only the last one. So the network at that time will go to S1 because S1 remembers only 1. So see how the table is very useful? Okay, so again, if I am in S4, if a 0 received, I will go to S2 because S2 remembers 1, 0. If a 1 is received, I will go to S1, so because S1 remembers 1, which is the first bit of the desired sequence. Actually, with this, we finish actually the derivation of the state graph. We did 2 examples, one with Mealy and one with Moore machine, and show you that the process is very simple, it's very routine, and it's very simple. And just you follow the guidelines, you can design any state graph for any problem statement. Okay, I thank you so much for listening, and please subscribe by clicking on the blue circle. Hopefully to see you soon in the next lecture. Sincerely, Dr. Hassan.